Hello, welcome to the Secrets of Calculus. This video is meant to start you on a journey that will explain what calculus is and quite possibly forever change how you see math. Oh, is this video too long? Here's the formulas. Let me know what you did with that extra free time. So fundamentally speaking, calculus is the study of infinity and its very, very strange behavior. Using infinity, we can decide when it's convenient to make things equal or not. And it's all encapsulated in the chillest operator you will ever see. Like all good math, we need to introduce a problem. So here is the problem. The functions are hosting a party. Only functions that are continuous are allowed in. And the current definition is you can draw the graph without lifting the pencil. It's got top shots like y equals 2x, x squared, and even functions like e to the x and sine of x. Some functions like square root of x bring partners, they're absolute values, and that's totally fine. But there are some functions that are excluded. These are the so-called rational functions, which have x's in the denominators of fractions. Now, if there's a possibility of that denominator being 0, that function is forced to deal with what I'm going to call forbidden values. For example, if f of x, y equals 1 over x minus 1, we must explicitly state that x is not allowed to equal 1. If it could equal 1, there's a potential for dividing by 0, which would create a black hole. Got it? Good. Now, forbidden values become really nasty when you're working with functions like g of x equals 2x times x minus 1 divided by x minus 1. Since the denominator could equal 0 if x equals 1, we must state this as a forbidden value. But the function wants to join this party, so it tries to use some algebra to get rid of the x minus 1. And it can do that. You can cancel out the x minus 1, except the forbidden value stays. And this is why functions like this, when they're graphed, have really awkward holes just in the middle of their graph. Now, looking at the graph paper, we can see that y would equal 2 if x could equal 1. But that's just because we can see that fact. The actual function doesn't know that. So we need a way, in order to get this y equals 2, we need a way to bypass this forbidden value, which, while still equaling 1 enough to actually provide a useful answer. And that challenge is answered by the limit. Here's how the limit works. The LIM spells out the operator. Below it are x, or whatever variable you want, c, the thing you want x to equal, and this arrow. In front of that limit, you have the function of that variable. The arrow stands for approaches, and it holds the key to unlock the limit, and ultimately, the map for the entire forest of calculus knowledge. When you read this out, it reads as the limit as x approaches c of f of x. Let's see it in action with the function we know can join the party, x squared. Sorry, x squared, we just need to pull you over to the side. Okay. Suppose we want to know what y was at x equals 2. So we set up the limit like this. Now this immediately tells us that we don't care what x squared actually equals at x equals 2. All that matters to the limit is what the function approaches. So for example, at x equals 1.9, y equals 3.61. And at x equals 2.1, y equals 4.41. This is not exactly a good estimate, but we can narrow down this search by using the idea that since 2 is between 1.9 and 2.1, the resulting y value is going to be between 3.61 and 4.41. This, by the way, is called the Bid Value Theorem. So let's try two other x values near 2. Say at x equals 1.999, y equals 3.996001. And at y equals 2.001, y equals 4.004001. So now we have a really close estimate. And once again, if x equals 2 is between 1.999 and 2.001, and also and so the y value is going to be between 3.99 whatever that is and 4.004 whatever that is. Now what the limit does is take this to the next logical conclusion. As we let x get closer to 2, the estimate for the y values gets closer to 4. Basically, it's finding the y value of x equals 1.9 repeating and 2.0 repeating 1. It forces us to ask the question, is 1.9 repeating actually equal to 2? The limit lets us decide on when it's most convenient to think of it as 2 and when to think of it as not 2. So in this case, I'd say it's convenient to think of it as equaling 2. When we plug that into the function, we get y equals 4. Now this might seem convoluted, but it solved the problem by bypassing any kind of forbidden value that we might have introduced. So let's go back to the older example of g of x equals 2x times x minus 1 divided by x minus 1. We want to see what happens when x gets closer and closer to 1. So based on this table we just made, we can see that as x gets closer to 1, y gets closer to 2. The limit basically says, well, try x equals 0.9 repeating. In this case, since it's convenient to think of 0.9 repeating as not equal to 1, we can still follow algebra's suggestion and cancel out the x minus 1 in the numerator denominator. And now, I can plug in x equals 1 and get an answer of y equals 2. But wait a minute. Why does that work? Didn't I just say that x equals 1 is a forbidden value? Well, here's the thing. This isn't really x equals 1. It's almost 1, but still close enough to be considered 1. Likewise, y is almost 2, but still close enough to be considered 2. That might seem really confusing, and it's actually one of the most confusing properties of infinity. See, when the limit gets us infinitely close to 1, the estimation error that comes with being really close to 1 but not actually equal to it, that estimation error shrinks to something so small that it becomes quote-unquote negligible. This has the side effect of making it so if you were to put it into a physical setting, no pencil is small enough to recognize this minuscule hole in the graph. Now, I want to make it clear that this cannot and should not be thought of as equal to 1. The limit simply allows us to treat it like a 1 when it's most convenient for us. It was not convenient to treat it that way before we removed the x minus 1, because plugging in 1 would result in a 0 divided by 0 situation. And now, with the limit seal of approval, g of x can join the function party because whoever hosted the function party did not define continuity very well. And now that you're armed with the knowledge that getting infinitely close to something is the same as equaling something when it's most convenient, and that the general trend can be assumed to extend, what do you think we can do for f of x equals 1 over x minus 1? I'll see you next time.